So where we left off last time was talking about crystal field theory and this idea that when we impose an octahedral ligand environment, we are going to have the 5d orbitals split into 2 EGs of higher energy and 3 T2Gs of lower energy. And we talked about the reasons why for that. And importantly, we called the gap between the T2G and EG orbitals delta O. And so now what we're going to talk about are, what controls the size of this splitting, the size of delta O, also known as 10dq. So that's what this slide is all about. And so there's a few things that can affect this. One is increasing metal ion charge. So as you increase the charge on the transition metal, you will increase the splitting. And so if you go from iron 2 to iron 3, you will get a bigger delta O. And this is because, right, you are pulling in the ligands with a more positive charge, and that causes more electron-electron repulsion, where this all comes from, this delta O splitting comes from, okay? So if you look at manganese 2+, hexaaqua manganese 2+ complex, it has a delta O of 8,500 wave numbers. You look at the +3 analog, much higher at 21 wave numbers. You can look at chromium 2, hexaaqua, chromium 3 is higher. Another factor is moving down a family increases delta O. And this is due to a similar reason as what we just said with increasing oxidation state. If you increase nuclear charge, because you're going down, there is more room, right? So one, more nuclear charge pulls in the ligands more, okay? That's one thing, but also there's more room because it's a bigger atom, so you can make shorter metal ligand bonds, okay? And those shorter metal ligand bonds will then have more electron-electron repulsion between the orbitals of the metal and the orbitals of ligand. That is what causes delta O to increase, okay? So you can look at ethylene diamine complex of cobalt, 3+. You can look at rhodium, and you can look at iridium. This I think this typo here should be 2+. But anyway, those are all in the same family, going down the periodic table, and so that causes the delta to increase, delta O to increase. Now, so we talked about basically changing the metal. What happens if you change the ligand? Well, changing the ligand has a big impact on the magnitude of the splitting between the EG and the T2G, the magnitude of delta O. And there's a certain order, and here are some ligands. There's infinite number of ligands, so these are just some of the most common ligands. But the same metal with these different ligands, carbon monoxide, will have a very large delta O. We call that a strong field ligand, meaning it strongly causes splitting. Something like iodide or bromide has a very, results in a very small splitting. So we call that a weak field ligand, okay? The problem is crystal field theory cannot rationalize this trend. If we were going to use crystal field theory to rationalize this trend, it should have to be related somehow to charge, right? We would expect more negatively charged ligands to have bigger delta O's, because more negatively charged would be more electron-electron repulsion, right? If we're just thinking about electrostatics. But you can see there's a negatively charged thing that is the weakest splitter, and there's a neutral ligand that is the biggest splitter. So this doesn't make any sense from an electrostatic model, which is what CFT is, okay? And so, yeah, why would carbon monoxide have a stronger effect than iodide? The answer has to do with the bonding of these different ligands. And in order to address bonding, we have to go to molecular orbital theory, okay? But before we get to that point, there's still a number of different concepts that we need to introduce that can be done in the context of crystal field theory. And so one of these is just the different electron configurations that are possible. Things get a little complicated here because we have two energy states, right? We don't have one. So if you have a D1 electron configuration, there's only one place to put that in the ground state. It's going to be in one of these T2G orbitals. And it doesn't matter whether on spin up or spin down or which one of these orbitals it is, XY, XZ, or YZ. Those are all degenerate states, and those are all ground states, right? We don't want to put that electron up in the EG. That's going to be higher in energy, clearly. That'll be an excited state. We're talking about ground states here. D2. D2, you're going to want to put them both in the T2G. Those are the lower energy orbitals. But you're going to want to follow Hund's rules and have those in separate orbitals. You want to maximize spin. If you put them together, spin paired, what is that going to do? That's going to increase electron-electron repulsion because you're jamming them into the same orbital. So that's going to be the ground state electron configuration. D3 is similar, okay? Now you have 3 all in different orbitals, maximizing spin. And that's the ground state. Once you get to D4, you have a choice. What do? Do you put an electron in a higher energy orbital? There's going to be a penalty for that. Or do you put an electron in the lower lying T2G, but spin pair? There's a penalty for spin pairing, right? Electron-electron repulsion. Here's higher energy molecular orbital, penalty for that. So there's energetic penalties no matter what you do. And the ground state, whether or not you're this state or this state, depends upon which penalty is less. So if your penalty for spin pairing is less, you will be in what is called the low spin state. Why is this low spin? Well, these spins cancel each other out, and so now you only have 2 spin ups. This is called a high spin state because you have 4 spin ups, right? So you have 4 spin ups here. This is the high spin state. This state will be preferred if your penalty for spin pairing is relatively large. Then you'll want to just go, your ground state will be putting that 4th electron in the higher energy EG orbital. Very similar thing for D5, right? Again, you can put the 2 electrons in the EG. All depends upon your relative penalties for spin pairing versus going to the EG. Or you can pair them up in the T2G if you have a relatively low penalty for spin pairing, and that will get you the low spin case, okay? D6 has the same high spin, low spin. D7 has the same spin, high spin, low spin. By the time you get to D8, you can't have high spin or low spin, okay? Because you're forced, no matter, even if you populate the EGs first, you're forced to put 6 electrons in the ground state. You can work through that, but you can try. Let's work through it just to see it, okay? And so let's say we want to do D8 here. So I'm going to do 2 examples. So I'm going to do 1. Let's try to make it high spin. So I go D1, D2, D3. High spin would be D4, D5. Now where am I going to put 6, 7, 8? I'm not going to want to put them in the EG. That wouldn't make any sense because that's the excited state. So I'm going to put them in the T2G. So I'm going to get that. Let's do low spin now. 1, 2, 3. Low spin means pairing up. 6, I'm at 6, and now I'm forced to put them in the high state. So, either way, once you get to D8, you can't have low spin, high spin. D9 and D10, same thing. All right? So you can think about how much energy do you stabilize just due to crystal field theory. And so basically that's worth 4 dQ for every electron that's in the bottom because the T2Gs are stabilized by 4 dQ. And then subtracting off 6 dQ for every electron that's in the top. So that's all that's doing. What determines high spin versus low spin? As we said, it's this stabilization energy being at a more stable state versus the penalty for electron pairing. And so in thinking about high spin versus low spin, excuse me, if you have a strong field ligand, strongly interacting ligands like carbon monoxide, cyanide, the ones at the end of that spectrochemical series, that's going to favor low spin. Why is that? Now you have a very large delta O because you have a strong field ligand. So that's going to make the penalty for going up into the EG very, very high. So that's going to favor you doing low spin, okay? Contrast, the opposite is also true, right? Weak field ligands are going to favor low spin because now you have a very small gap, and so it's not a lot of energy to populate into that higher EG state. Higher oxidation states are going to favor low spin. Why? Because higher oxidation states have a stronger delta O, okay? And second and third row transition metals are almost always low spin, it turns out. And again, that's just because the second and third row transition metals are bigger, and because of that, they pull in, they have more steric room and more nuclear charge to pull the ligands in closer. That gives rise to bigger delta O, as we talked about earlier in this video. All right, so that's where we're going to end up. And next time we're going to look at tetrahedral symmetry, what happens there. So far, this has all been octahedral.